Okay, thank you very much, Yvonne. That was, I hope folks, you can see now that ellipsometry is hugely powerful, that we can measure N and K, or psi, what we measure, as Yvonne said, was psi delta, but we can then transform that into N and K, and then, as I'm suggesting, we can build physical models around this. I would like to emphasize the last thing Yvonne said, though, because it's important. If you don't care about the underlying physics, you probably will get a better fit to many peculiar materials if you have a completely sort of non-physical but Kramers-Kronig consistent model. So all you're doing is just saying, here's a function that describes N and K, and it's consistent with those Kramers-Kronig transformations. So I'm presenting to you perhaps quite a pure way of thinking about this, in saying I am interested in the band structure of my material, and I will build my model around what I know about the band structure. You can just step back from that and say, I don't care, or maybe I don't even know, and I don't even have any ambition to know what my band structure is, but I just want to be able to get a parameterization for my N and K, because I then want to go away and measure thickness or something using it, and that's perfectly okay. But what I want to do is to bring us back and talk about modulation spectroscopy, because I hope can see from what Yvonne's presented that if you've measured data using ellipsometry experiments, you've got a huge number of parameters to fit. And it's quite possible that when I showed you this gallium arsenide absorption coefficient with those little arrows on it, you thought, okay, that's nice, you fitted a model to your data. But the features there aren't very strong. I mean, so, you know, there's a kind of slope there, and I'm suggesting that there's 3 electronic transitions responsible in that slope. And even when we look at N and K, it's not that obvious that there are actually 3 transitions there. And that's where modulation spectroscopy comes in, because modulation spectroscopy can really nail exactly where those band edges are. And then you can come back to your ellipsometry fitting and say, right, I really know what my band gap is, I know what E1 is, I know what my spin orbit band is, bang, 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 fix those, and then the optimization software that Yvonne's just shown you can help fit the other parameters, like the broadening parameters, which you might not know so well. So first, I just want to start with something that's probably familiar to many of you, which is this Tauc plot for determining band gaps. And it's perfectly valid. It was proposed in the late 1960s and is often applied to disordered semiconductors. So if you plot the photon energy multiplied by the square root of epsilon 2, you will get a straight line, and there's various assumptions behind that your bands are sort of somewhat parabolic and so on. This is fine, and the idea here is that the band gap energy is where this linear part of your data hits the x-axis, and that gives you an indication of your band gap. As a graphical construction, this works, but as was pointed out by some of our colleagues a year or 2 ago, and unfortunately the reference has gone off the screen, I apologize for that, it only works in three-dimensional semiconductors. If you're looking at nanocrystals or something, you can't expect to be able to make this plot and get a reliable indication of the band gap. So, how might you do this? Let me show you, first of all, the result of modulation spectroscopy. On the top is the reflectance from gallium arsenide. So that's just the reflectivity, plotted as a function of energy. On the bottom, we have the results from an electroreflectance measurement. And I still find it absolutely astonishing that this method can nail, if you notice, E0, E1 plus that spin orbit band, E1 and higher lying bands. And so what you're doing with this measurement is you're modulating the refractive index of your material. It doesn't actually matter how you modulate it. So the term modulation spectroscopy means you just somehow change the optical properties of your material. So you can do that, as I'm about to show you, by applying an electric field. You can do that by pumping electrons into the material optically. You can do it by changing the temperature. You can do it with vibrations, with a piezo vibrator. There are many, many different variants of modulation spectroscopy. But I'm going to show you electroreflectance, which is one of the most successful and widely used methods. And what you're doing is you're just doing a reflectivity measurement. So here's a lamp and a monochromator, so you're just shining light onto a sample and detecting the reflected signal. But what you're doing, though, is that material, in this case, could be a p-n junction, it could be a Schottky diode, and you're modulating the applied voltage across that material. So in other words, the electric field inside it is changing constantly. And then what you do is you use a lock-in technique similar to what Ivan, in fact exactly the same as what Ivan described when he was talking about the spectrophotometer. You look for a signal in the reflected signal at the frequency of the modulation. And what you find is that where you have band edges, so where these oscillators sit, that's where the effect of the electric field changes the reflectance. So away from where the oscillators are centered, you don't get any change in the reflectance with the modulation. But at, if you like, the resonant frequency, or the resonant frequency in this case being an energy, a photon energy, then you see a little shift in the optical constants, and you see that as a change in reflectivity. So notice this scale. The scale, this delta R upon R, is a change in reflectivity, and this is times 10 to the 3. So this is actually quite a small reflectance. So if you just go upstairs and do a measurement of a solar cell and you put a reverse bias on it, you're not going to notice a difference of 10 to the 3. But you connect a lock-in amplifier up to this, and this is exactly what you'll be measuring, is this electroreflectance signal. And I hope you can see that this could be remarkably useful because it really identifies these so-called critical point energies very, very accurately. You can do the same or very similar with with something called photoreflectance. So with electroreflectance, you need usually to make physical connections. So you've made a diode or you've made some kind of Schottky device, you've put metal on your material. The nice thing about photoreflectance is all you need is a sample. And then the idea is very similar, but now instead of modulating the field using electrical bias, instead you have a chopped laser or chopped light source. And so it's a very similar type of measurement. You have here your reflectivity set up, and what you're looking for is for a signal in that reflectivity, in the measured reflectivity, that corresponds to the chopped laser frequency, because that's the modulation that you're applying to the material, and that, just as in the case of electroreflectance, is going to shift the frequency of those oscillators just ever so slightly, and you'll be able to detect that. Photoreflectance, though, is a much harder measurement to set up. So if we set off this afternoon and said, okay, we're really excited, we're going to do electroreflectance, I reckon by the end of the day you'd have it running. If you try doing photoreflectance, it's a lot more tiresome. And for many of the reasons that Torsten described this morning, you have here a laser that has to be relatively intense, so we're talking sort of a few milliwatts, which excites the sample. You may well get photoluminescence. That can perturb your signal here, so you're going to want to have a filter. You may get scattered light. You're going to want to have the filter for that too. So photoreflectance can be a little bit harder to set up, but it's actually a little bit more versatile in that you can just make a material and then measure it. You don't need to make electrical contacts. So to finish with, I just want to show you an example which in my own research has been very useful for a great example of photoreflectance. And once again, we return to this problem of how can I make a 1 electron volt material in a multi-junction cell. And one of the other candidates, if instead of putting bismuth into your gallium arsenide, you put nitrogen. Now nitrogen does something unusual to the conduction band. Here we have the dispersion in the conduction band, so we've got energy versus wave vector here, and the black dotted line is what you'd expect for gallium arsenide. If you add nitrogen, it introduces a nitrogen defect level that actually lies within the conduction band, and so the effect of that is it splits the conduction band. It splits it into a upper branch, which we call E+, and a lower branch, which we call E-. So technologically, this is useful because it can reduce the band gap of gallium arsenide very, very quickly. You add more nitrogen, the more splitting you get, and that's exactly what you can see here in this graph. So very much the same sort of motivation as we're looking at with bismuth. Band gap goes down remarkably quickly. We're interested in 1 electron volt alloy with about 4% nitrogen, we'd be there. Of course, what we're measuring here, so these data points, for example, you might get from PL or some kind of technique that gives you a band gap, a good measure of the band gap. But the interesting aspect of this, or at least I think it's interesting, is instead of just reducing the band gap, you're actually splitting it. So you're pushing half the states up in energy and half the states down. So let's do some modulation spectroscopy. Here, this is a photoreflectance signal, so all we've done is grown this material. We haven't made any contacts, we haven't done anything, and on the top we have the signal from gallium arsenide, okay, 0% nitrogen, and we have a very strong E0 transition, and here's spin orbit, and here's E1, okay, at some higher energy. As I start putting nitrogen into this, what do I see? Well, I see here's E-, and here is E+. And so you can literally see the splitting of these bands directly in the photoreflectance spectrum. And then, you know, we add more nitrogen, the splitting gets bigger, and I mean, just for fun, we're measuring E1 here, and we see that E1 doesn't change very much. So from a, you know, relatively simple optical measurement, we can get really important information as to what's going on in our material when we're adding, in this case, nitrogen. So that brings us to the end, and I thought I'd just have sort of 3 take-home messages. One is that I hope what Ivan and I have presented to you today sort of has driven home this notion that we can describe the optical properties of materials with the complex refractive index, that, and that's conveniently parameterized with N and K, that we can measure N and K using a variety of reflective techniques, something as simple as a reflection measurement, or if you prefer, sort of something sort of effectively a polarization and angle of incidence dependent measurement, which is what we call ellipsometry, and that we can use models then to extract valuable information out of that with respect to the band structure. And then finally, that we can use techniques like modulation spectroscopy to really nail down where these optical oscillators are sitting in our semiconductor material. So thank you, everyone. I hope this has been useful. I think we have maybe a few minutes for questions. And
first,
yeah.
let's thank Natalie.
Thank you.